All
We
right.
should turn this into the spelling bee class. That should be what we do. Dang it, I'm not going to be there for that.
All right, so today we're going to talk about how to find eigenvalues ourselves. Okay, so let's consider how to find the eigenvalues of this matrix. And so what we want to do is consider solving the equation A minus lambda I x equals 0. So if I go ahead and calculate A minus lambda I, and then solve this equation, okay, so I'd probably go to echelon form to solve the equation. So, I'm sorry, not echelon form, but augmented matrix form. I don't know why I even wrote this in the meantime, but that's okay. So, if I were to solve this particular augmented matrix, what am I looking for the result to be? Mark? Yeah, so you're solving for a non-trivial solution. So personally, I do not want to do row reductions with expressions with lambda. Because when you think of trying to cancel out the 6, you'd have to multiply the bottom row by -4 minus lambda, or scalar multiple of that, and then the top row by 6. And that's rough. All of a sudden you have all these things to keep track of. So what else could we think about in terms of solving this without doing elementary row operations that have lambda in them? Yes?
You could have like 2 equations, like -4 minus lambda, and because we need that term to equal 6 and the bottom term to equal -1, and hope that we get the same lambda value for each.
You could, for sure. But also thinking of it in 3x3 land, that would get even more challenging.
Not really, it's like, well, like, just like based on, I don't know, because what we need is, because we need a row of zeros, at least that's what I'm thinking, so if you get the bottom and top to be 6 and -1. And
No, I'm saying yes and 2x2.
Right, but it should still work with 3x3.
But think of what you'd have to accomplish to get that row of zeros.
Oh, okay.
So I agree, but
Yeah.
just as a different thought, yes. If this has a non-trivial solution, what's going to be true about this matrix right here? The determinant is 0. So generally, it's easier to solve knowing that the determinant of A minus lambda I has to be 0 if there are eigenvalues.
That wouldn't tell you what they were, but if there was confirming this.
No, it would.
It does.
You like multiply -4 minus lambda by 1.
And then you add 6, and then you set that to 0, and then it's like lambda.
So the determinant would be so we'll set that equal to 0.
Plus 6.
It's normally
minus negative.
Oh, right.
Okay, what happens? Oh, that's.
Did I do anything wrong here?
Is that plus 3?
Yeah. Oh, negative times a negative is positive, just FYI.
Whoa.
Sorry. Okay, so then we get lambda plus 2, and lambda plus 1 is 0. So our eigenvalues are going to be negative 2 and negative 1.
Oh, I can see one here.
So those are our eigenvalues, and given our eigenvalues, we could then find the corresponding eigenvectors. But we already got that homework last night, right?
Shoot, that would be done
Lots
with the
and
terms
lots.
for 3x3s.
But we know how to do that.
So many times.
Also, yeah, but Jeff is right. It takes time.
Yeah, but you have lambda in there. So.
Yeah.
Okay. So we talked about how elementary row operations can affect determinants. So remember, if you do row exchanges, it makes the determinant negative. So if you have a number of row exchanges, the determinant can vary by plus or minus. And then if A is invertible, then basically you're not going to have eigenvalues because the determinant will not be 0. Questions? Okay. So we know that if we do elementary row operations, the correct ones, the determinant, as long as you don't scale any rows, the determinants will just vary by being plus or minus 1, and the determinant will be 0 when A is not convertible. So that is all a review of how determinants are affected by elementary row operations. So we are adding to our invertible matrix theorem, our last 2 bullet points to get us through T in the alphabet. Almost got all the way to Z. We didn't get quite there.
Counting on me later. 11 before Z.
That is 6.
Okay, so 20. Okay, so 0 if it is invertible.
Every time.
You have to check that.
Okay.
That would be more than 6.
Yeah, it does make.
U, V, W, X, Y, Z, that's it.
I
I know the alphabet.
Yeah.
Are there more this year? Or is it you just have
Can
to
you
C, or
A,
like
C,
you do like AA or what?
I feel like this is it, but I'd have to look into it to see if it gets any further.
Subscript letters.
All right.
What is the rest of the way up to that? Is it just like this chapter, or is there like more actually?
Oh, there's more. We just can't get to it. We run out of time.
So I feel like there should be more.
We can look. I mean, the textbook is all in there. All right, so check this out. And don't confuse this. They're discussing the matrix A, not the matrix A minus lambda I. The matrix A minus lambda I is going to not be invertible if there are eigenvalues. Okay? But they're just talking about the matrix A, not A minus lambda I. So if A is invertible, 0 is not going to be an eigenvalue. Also, the determinant of A is not 0 if you have an invertible matrix that we've been talking about for long, but it's the last one. Well, it might keep going, who knows?
But like, come on.
Yeah,
Actually, it's not about you.
I do. We're all like mediums or larger, so you guys might need some more time.
I don't work meetings.
But we literally
I can
did it
ask
for
her.
like 5 minutes. Let's take a picture at the end of the day.
Tomorrow?
Yeah.
Okay, I'll write myself a minute.
You don't.
You need 2 t-shirts?
So any,
Wisconsin.
upper body,
But I have my coat. Do you wanna wear that?
Actually, I can have this runner.
that seems like a liability for me. I feel like I would accept it.
Okay, well, my kids have
And
mediums.
if it's just a t-shirt, that is, oh, well, very sorry for that, okay. Thank you then.
Okay, do you still need one or no?
Right, I have a coat.
I'm good.
They don't want my stuff, but that's
How many did
fine.
you,
I have plenty. I think I went to Madison.
we asked for 1 each.
Yeah, that's fine.
Okay.
Okay.
We need a apron too.
What?
Okay. We are recording now. All right. All right. It's not the start, it's the middle. Okay, we all know about these properties of determinants, that if you factor a matrix, the determinants are going to be the product of the 2 matrices. We know the determinant of the transpose equals the determinant of the matrix. We know that if the determinant is 0, it's not verbal. This is something we talked about when we did our determinants chapter, the fact that if you have a triangular matrix, the product of the entries on the main diagonal is going to be the determinant. And then row replacement doesn't change the determinant. Row exchange changes the sign. Row scaling scales the determinant the same as it would scale the row. So if you double one row, the determinant would be doubled. Okay, so now we have what is called the characteristic equation. This is the title of today's lesson for those of you that may have forgotten 10 minutes ago. So, when you write the equation that we wrote to solve and find the eigenvalues, which is setting the determinant equaling the determinant of A minus lambda I equal to 0, that particular equation has a special name, and it's called the characteristic equation. So the characteristic equation of a matrix is yet another quality that square matrices possess. Every square matrix has a characteristic equation. And the quantities that solve that matrix for lambda are the eigenvalues. And we talked about why that would be true.
That's a very brief update. In 7.4, there's root through x. We were which
All the way to x, so it doesn't end on.
Rule on. How many letters left is that?
well, at least not. I know you're all
It's a
wondering.
big up one. Not something, I couldn't.
I see you're diligently taking notes, so I want to support that.
That is a good question.
Hey, quit laughing back here.
All right, so let's find the characteristic equation of this 4x4 matrix. One beautiful thing about the 4x4 matrix is that it's an upper triangular matrix. And so it is much more straightforward to find the determinant. So we're going to have to find the determinant of A minus lambda I and set it equal to 0. So A minus lambda I and the top we don't really care about. We'll write it down just to be a little more complete. Oh, holy cow, what happened? So the determinant of that matrix equaling 0 would be 3 minus alpha, lambda, negative 4 minus lambda, 3 minus lambda, or I could have just squared that, let's do that, and then 7 minus lambda is 0. That is the characteristic equation.
Oh, that's pretty cool.
So every square matrix that's 2 by 2, we do a 1 by 1. I don't know if that makes any sense. I'll just say every square matrix has a characteristic equation. So we could also write the characteristic equation all the.
What's the significance of the square? What is that? It's just
It was compared to it.
Yeah.
Just move with it. Yeah.
Thank you.
It's not everything.
So this thing's for the.
Wait, hold on a second. Didn't we already say that in row echelon form, the eigenvalues are just like rows anyway?
Yeah, that's why.
So this is kind of pointless.
Well,
No, we're naming the characteristic equation. That's the goal of this. I'm not solving, I'm writing the equation.
Okay.
I know how to spell it. Yeah.
that means that for any m by n, you can just split it into an LU and do this multiplied by the matrix with the characteristic equation.
Yes.
That's pretty simple.
Didn't you say before that you like do things to the eigenvalues and do row operations without changing them?
Otherwise,
So you have to keep track
That's the point.
of the changes that would occur.
I understand.
All right, so if you multiply that out, and you put little lambdas in here, that would be what you get when you multiply it out. So when it's all factored, it tends to be called the characteristic equation. When you multiply it out, we call it the characteristic polynomial. And it's more in standard polynomial form and not factored form. Yes?
Why would you want characteristic polynomial?
I feel like you never would want kids.
Well, it's easier to identify the degree.
Right. I feel like it's not that hard to identify the degree.
It's not, that's why I'm in case. Yeah, I have no idea why you want to do that.
Okay.
Maybe if you're given the characteristic polynomial.
You got this back.
You got it back. Wait, you have the rational root theorem.
I know, that's a stupid Peter there, Margaret. It was the worst. That's where synthetic division became useful for like 1 second. I don't know around.
Well, we're gonna relearn.
It's also useful
All right, circling back to what we're doing. Okay. So in this characteristic polynomial, we did have the factor lambda minus 3 come up twice. And so different eigenvalues can have multiplicities other than 1. And so that means the eigenvalue occurs twice for 2 unique eigenvectors. I don't know why I'm doing it. Let's do it this way. It looks less. Okay.
So multiplicity is like a degree except for how many times the same thing.
I do remember that.
Yes.
I remember they create some balance like that.
Yeah, yeah.
Just kind of,
It's like
Yeah,
a-
okay.
It's
Double
like a
or
multiplicity
triple
of
root?
3, no, it's like the.
It is 3, then it's 5, so
Yeah.
I think it's 4, and then
Yeah, every column.
All right. Mark, to get you from stopping talking, I'm gonna have you read this.
oh, sick.
What? Come on. I've been taking notes the whole time.
Rohan, poor
Did you hear why I wanted to do it?
Because he's not paying attention.
Yes, it's a redirection. Go ahead.
It's like a reward.
Yeah, that's right.
I never listened.
The characteristic equation is important for theoretical purposes. In practical work, however, eigenvalues of any matrix larger than 2 by 2 should be found by computer, unless the matrix is triangular or has other special properties. Although 3 by 3 characteristic polynomial is easy to compute by hand, factoring it can be difficult unless the matrix is carefully chosen.
Okay. So now we have another definition.
I love it. Yeah.
A and B matrices. So you know how in triangles we have similar triangles?
Yeah.
Well, now, thank you, Alex. No, you're like with me. So a similar matrix, or two similar matrices, are matrices that have the same characteristic polynomial. And so if they have the same characteristic polynomial, they have the same eigenvalues with the same multiplicities, because the solutions of the characteristic equations will be the same. So let's determine whether the two matrices are similar. What are the eigenvalues for the first matrix? 2 and 2. So 2 with a multiplicity of 2. That's weird, multiplicity of 2. And then this is 1 and 2. Therefore, not similar.
That is that rewarding.
My God.
Wait, it's not recording.
Oh no, that is so mean.
My dog's flying up.
And two. Got it. Okay. So, okay. Now let's read point 2. This is important. And this relates directly to what you talked about. So similarity is not the same as row equivalence. All right. So if A is row equivalent to B, then B equals EA, where E is writing all those elementary row operations as matrices. Do you remember that we could do that? Represent every row operation as a matrix. So E is the product of all those row operations. Yes.
If you do it like that, can you find the new eigenvalue by just looking at the lambda values or the eigenvalues for both the E and the A?
I have not tried it.
I guess you'd probably end up with like 3 twos or something.
Because if,
You'd end up with like 1 and 2 twos at the very least.
and let me just look at this. A thought I had. Mark, I see your hand. I'm going to call it very shortly.
Okay, fine.
So let's say that the C is more.
Okay, yeah, I'm not sure.
It was, I mean, it was due yesterday.
For a long of it, yes.
So like, we did determinants, and like we did row operations to determine like the new determinant and how you link it back to the old one. Can you do that with eigenvalues?
Yeah, I don't know.
Okay.
That was the same thing that I
Oh, really?
Yeah.
Oh, my bad.
asked. That's okay. Yeah. It usually changes in the values, but I'm not sure how. I'm just thinking, like if you have an upper triangular matrix,
I can't see the board otherwise.
Give you glasses. You're gonna this whole year.
I'll get the glasses like whatever.
okay.
Whatever.
You leave school for a haircut, but
Dang.
I wanted to take longer than
You didn't even have it today.
you leave school for a haircut. All
Well,
right.
I was supposed to have a haircut, but my mom screwed it up.
Sure.
All right.
Wow, your mom so organized, believe it.
What?
Isn't it like not very relevant? Like P inverse times P is.
No, this gets very relevant, especially for what's coming. Okay. Okay. So, if A and B are similar, the following are true. Okay? P inverse times A times P equals B. Yes.
So it's-
So the P and the P inverse not cancel because there's a B in
So is matrix multiplication commutative?
Okay.
No. So that's why A and B are not equal necessarily. I mean, certainly they could be, but most matrix multiplication is not commutative, so you can't just switch the order of the things.
Is P just in very similar to that?
So we're gonna learn how to find P. P is a special matrix. But we can also write, if this is true, P inverse times A times P equals B, we can left multiply both sides by P, left multiplication, being careful to do that, then you get AP equals PB. So there is a matrix P such that right multiplying by A equals left multiplying by B. We're going to talk about how to find P and how it relates to the eigenvalues and the eigenvectors. Okay, because those are very close relationships there. And when you transform A into B, and we know B is P inverse AP, it is called a similarity transformation. Yes?
Why second bullet point?
Yeah.
Okay. They're saying,
Change the letter.
okay. So you guys remember the double arrow?
Okay.
Yes. So the arrow that looks like this.
Oh, no, yes.
So that means the single arrow means implies. One thing implies the other. The double arrow is a double implication, meaning you can say the converse, and the converse is also true. So what the second bullet point says is that A and B are similar to each other. It's not a one-way street, it's a double-way street. So just like in inverses, if A and B are inverses, they have to be inverses of each other. So A is B's inverse and B is A's inverse. It goes both ways.
I'm more confused on why it's Q.
Because
You guys make it very clear.
it's not the same matrix as P. Q and P would be inverses of each other.
Oh.
But couldn't you?
So you don't want to have the same letter meaning different things on one page.
Fair enough. That is,
Because it's, Ray, BQ equals QA. Did I write that? Okay, yes. So notice P and Q are not equal.
Yes. But you could just wrote P, B, P minus 1. Okay, never.
You could have, but then it'd be a lot of inverse notations.
Did Riz the same amount?
So they just wrote it backwards, but stuck another letter in between.
Because they aren't the same, they aren't the same matrix. They can't be the same letter.
Step 1 is 2 is 3.
All right.
I'm surprised I did.